And you're gonna see a lot more examples in your notes than you normally do because there's kind of a lot more to work through and a lot more small details that we have to consider when we're doing this. So I figured I'd build in more examples into the notes than I normally do. So if you have like denominators, if you have common denominators to begin with, it's just like adding regular fractions. All you have to do is add the numerators together, and that's it. In this case, it would be like combining like terms if you can, but if you take a look here, x plus 4, the denominator is already the same. So all we need to do is add the numerators together and get x plus 5 over x plus 4. And that would be the answer. That's all we'd have to do for this particular problem. That's the answer. And it shows it again right here. So same thing. So the same idea happens with this next problem. It says to multiply the factors in the denominator because while these are currently written differently, those denominators are the same. And we can do that by distributing the x into the binomial here, x plus 3. So let's go ahead and rewrite this problem, but distribute the x into x plus 3. And so we're going to get 2x plus 1 over x squared plus 3x plus 3x minus 8 over x squared plus 3x. If you distribute the x into the denominator on that second fraction, it ends up being pretty obviously a common denominator. So we don't have to do anything about finding a common denominator here. All we have to do is combine like terms on the numerator, and that's it. So we're going to add 2x and 3x together to get 5x. We'll take 1 and we'll add -8, or we'll take 1 and subtract 8 to get -7 over x squared plus 3x. And that's the answer. If we could factor the numerator, then we would also factor the denominator to figure out, if there's anything that could cancel out. But because the numerator doesn't factor, there's no sense in factoring the denominator because we're not going to be able to cancel anything out. Now, if we wanted to, we could also, it doesn't ask us to do this on this one, to talk about values of x in terms of the domain like we did yesterday. But if we were talking about values of x like we did yesterday for the domain, we would say the domain is all real numbers except for x equals 0 and x equals -3. Because those are the values on the bottom that make the denominator equal to 0, in which case we can't have values there on the x-axis. Any questions about that one? Okay, I want you to try 1 and 2 on your own then. Same types of questions that we just did. So, like I said, it's a little deceptive with these first couple ones. They seem pretty straightforward because they are. But the complexity does ramp up pretty quickly. But try A and B down here real quick. And if you find anything that you can factor and cancel out, definitely do that. I don't think that happens on either A or B, though. Those should be our answers right there. Just combine your like terms on the numerator, keep the denominators the same. That's it. Nothing to it. So any questions on these before we continue? Because as soon as we start having to find common denominators, that's when this process becomes a lot more than what we just did. So if there are any questions now, definitely ask. If this isn't making sense, the next page will be a bit of a stretch. It might be a bit of a stretch anyway. All right. It's more interesting though this way. All right, so first thing we're going to do, we're not actually going to be adding fractions yet. We're just going to be talking about finding least common multiples. So we're going to have two different expressions here. And we're going to try to figure out what is the least common multiple between those two. Now, in order to figure out multiples, we're going to need to factor them because when you factor something into a binomial, each binomial is a multiple of the particular expression. So, for example, this one is technically already factored, but let's write it in not standard form, but like expanded form. So x plus 2 times x plus 2. So this first one, we're going to say x plus 2 squared equals x plus 2 times x plus 2. Just like that, write it out twice. And then the next one, x squared plus 5x plus 6, factors to what? 2 and 3. Good. So x plus 2 times x plus 3. So now that we have these factored, we're going to compare x plus 2 times x plus 2 and x plus 2 times x plus 3. The least common multiple is the product of the factors. Include the greatest number of any one factor in each polynomial. So basically what we're looking at is, because they already both have at least one x plus 2, the numerator, not the numerator, but the top expression here does not need an additional x plus 2 to multiply onto the end of it to create the common multiple. Likewise, down here, this expression does not need another x plus 3 multiplied to it because it already has one. This one doesn't have an x plus 3, so this one needs to be multiplied by x plus 3. This one down here only has one x plus 2, whereas this one has 2. So the one down here needs to have an additional x plus 2 multiplied onto it. So what we're going to look at here is, so for the top one, we're going to say x plus 2 times x plus 2, and I'm going to put this in a different color to show you exactly what's going on with it, times x plus 3. And the one on the bottom, I'm going to write x plus 2 times x plus 3. And then in a different color, I'm going to multiply by another x plus 2. So now they're both the same because they both have the same things that are multiplying together. 2 sets of x plus 2s and 1 set of x plus 3. So if you multiply all 3 of those together, you would end up with the exact same expression because they all include the same factors. Does that make sense? There's an example just using straight up numbers up here. 6 and 15, right? 6 breaks down into the prime factorization of 6 is 2 times 3. The prime factorization of 15 is 3 times 5. Each of these already has a factor of 3. One has a factor of 2. The other has a factor of 5. So that means that this one needs to multiply by a factor of 5. And this one needs to multiply by a factor of 2. Which means the common denominator is 30. The least common multiple between those 3 is 30. Because if you multiply 2 times 3, which is 6, times 5, you get 30. And if you multiply 3 times 5 by 2, because that's the one that's missing, you end up with 30 for each one. And we're doing the same thing over here. We're just using binomials instead of just straight up numbers. So let's take a look at the next one. And then have you try a couple on your own after that. So we're going to have x cubed minus 9x. What's that going to equal? What can we factor out of those two? Okay, because when we factor out the x, which we'll do first, that'll give us x times x squared minus 9. And then you're exactly right with the next thing, because this is a difference of squares. So this can actually factor more. So that's going to equal x times x plus 3 times x minus 3. Nice. And then the other one, actually there's 3 of them this time. So we're going to factor 3 things. So we're going to get x squared minus 2x minus 15. X squared minus 2x minus 15, that's going to be what? Negative 5 and positive 3? Does that sound good? X minus 5, x plus 3, okay? And then the third one is x squared minus 5x. So we're figuring out a least common multiple for 3 expressions this time. So x squared minus 5x, we can factor out an x from that one. So that'll be x times x minus 5. All right. How many distinct polynomials do we have here? We've got x This one doesn't have x, this one does. So the middle one will definitely have to be multiplied by just x. This one has x plus 3. So does the second one. The third one doesn't, so the third one needs to be multiplied by x plus 3. X minus 3. This one doesn't have x minus 3, so that needs to be multiplied by x minus 3, and so does the bottom one. And then the other one that isn't included here, that is in the other two, is x minus 5. Both of the second two have x minus 5, but the first one doesn't. So the first one needs to be multiplied by x minus 5. The second one needs to be multiplied by x and x minus 3. And then the third one needs to be multiplied by x plus 3 and x minus 3. So we're going to end up with 4 things that make up our least common multiple. We're going to have x, x plus 3, x minus 3, and x minus 5. So we're going to say the LCM, least common multiple, is x times x plus 3 times x minus 3 times x minus 5. That is our least common multiple. We could have written it out like we did on this problem here, but we're going to do that here instead. Something that you can consider if you're having a hard time, because there tends to be, like, with this kind of stuff, there tends to be a lot of overlap. There's a lot of overlap between similar things. And so if you want to, if you have like highlighters or something like that, you can use highlighters. And you can just highlight the things that are the same. So here's x, here's x. Here's x plus 3 right here. And another x plus 3 here. I don't see any others. We've got x minus 3 here, which doesn't exist anywhere else. We've got an x minus 5 here and an x minus 5 here. So we're basically looking at, like, how many different colors are there? There's 4 different colors, which means our least common multiple needs one of each of those. So that's another way you can think of it, is if you separate it out by colors, sometimes it can be a little bit helpful that way. All right, I want you to try A and B on your own down here. Same type of problem. So figure out the least common multiple for A and B. I'll work on it on my paper. I'll move my answer out of the way for now. Come back in a couple minutes and see what we get. And fill that out as well. All right, so with A, I apologize. A has something that I realized that I don't think has been taught to you yet this year. And that is the cube of a polynomial. So if you started like I did to factor it by grouping, you probably figured out pretty quickly it doesn't factor by grouping. So this one here, write this down onto the side, cube of a polynomial, because that's what this turns out to be. The cube of a polynomial is x cubed plus 3ax squared plus 3a squared x plus a cubed, and those four terms factor to equal x plus a cubed. What that means is, if your first and your last terms are perfect cubes, especially the last term, if it's a perfect cube, if you cube root the last term, that becomes a. And then you can test it with the rest of this function to see if it actually works, and this one does. So for example, the cube root of 27 is 3, right? Because 3 times 3 times 3 is 27. And so if a is 3, and you try it with this function here, 3 times 3 is 9. The second number here is 9. 3 squared is 9. 9 times 3 is 27. The third number is 27 with the x after it. And then 3 cubed is 27. Yeah. What's that? So if you know the first term and the last term, if you have a 4-term polynomial, like a cubic 4-term polynomial, and the first term is a perfect cube, cube root of x cubed is x, the cube root of 27 is 3, because 3 times 3 times 3 is 27. So if both of those are perfect cubes, then you can test it to see if it is the cube of a polynomial by the cube root of this number is going to be a in this particular function. And so if you take the value of 3, the cube root of 27 is 3, so a is 3. So if you plug in a here, 3 times 3 is 9, so that should be 9x squared for the second term, and it is. If you plug in 3 here, 3 squared is 9. 9 times 3 is 27, so we should have 27x here, and we do. And then 3 cubed is 27. So what this can factor to is x plus a, or 3 in this case, x plus 3 cubed. So the first one, this ends up being x plus 3 cubed. That's what that first one factors to. So I didn't even notice that there was a cube of a polynomial here. All right. And then the next one, this one should be a little bit easier. What does that factor to? Anybody get that second one? Yeah, x minus 7 and x plus 3. All right. So what will our LCM be for this one? What is our least common multiple? How many factors of x plus 3 do we have to have? We have to have 3 of them, which means we need to add 2 of them to this one. We got to have 2 of them here, so there's going to be a total of 3. And then we also have to take x minus 7 and multiply it by the top one. So basically, we're going to get x plus 3 cubed times x minus 7. That is our LCM. Because the top one here, the first expression has x plus 3 cubed, which means we don't need to put another x plus 3 multiplied into it up here. We need the x minus 7 because that's what this one doesn't have. And the one on the bottom here, the second expression, has the x minus 7, but it only has one factor of x plus 3, so it needs 2 more in order to get to our least common multiple. So that is our least common multiple. Hopefully B was a little bit easier. This one looks to be entirely, yeah, this one's entirely trinomials. There's another variable here, but that shouldn't change things too much. So let's see what happens. What can we factor out of this? 10, all right. So that'll be 10 times x squared minus y squared. That is the difference of squares. So this is going to actually equal 10 times x plus y times x minus y. So the first expression turns into 10 times x plus y times x minus y. The second one, that looks like a perfect square trinomial. No, it's not a perfect square. Well, it will be a perfect square trinomial, I think, once we factor out the 15. So factor out of 15, that'll give us x squared minus 2xy plus y squared. And that is a perfect square trinomial. We're going to get 15 times x, let's see, was it x minus y and then squared. Sorry, I'll scoot that up so you can see it. Because x minus y times x minus y equals x squared minus 2xy plus y squared. This term is a perfect square, that term is a perfect square. And if you can square root both of those, the coefficient in front of this last term would be 1. And if you double 1, you get 2. And if it's a positive 2 or a negative 2 here in the middle, that means it's a perfect square trinomial. This minus is what determines that minus there. If this is a plus 2 in the middle, this would be x plus y squared. But because it's a minus 2 in the middle, it's x minus y squared. It's similar to if you have something like, let's say, x squared minus 8x plus 16. That would be x minus 4 squared. It's a perfect square trinomial is what that one's known as. So we've definitely dealt with this kind of stuff before. We just haven't done the cube of a polynomial before. All right, and then the last one, x squared plus 3xy plus 2y squared. So two numbers that multiply to 2 and add to 3. 2 and 1, yeah. So that'll be x plus 2y times x plus y. All right. So I'm going to actually use some colors here. So let's see. 10 and 15, all right. So we need a least common multiple between 10 and 15. That's something that has to happen. What's the least common multiple between 10 and 15? 30. All right, so let's start with that. LCM equals 30. We need 30. Let's see. How many x plus y's do we need? I think we need 2x minus y's, but x plus y's, how many do we need? Because the only thing squared here is the x minus y. That one has a single factor of x plus y. This one has a single factor of x plus y. So we only need one of them. So x plus y. We do need x minus y squared because we need both factors of that. And we also need the x plus 2y because that's a different one altogether. So x plus 2y. So there's our least common multiple for those three. Any questions about that before we move on? Because this is the process we're going to use for finding common denominators when we actually add and subtract unlike denominators with rational expressions. So this, what we're doing here, this will be a portion of pretty much all the other problems that we do from here on in. I think you're starting to see why this is going to take us 2 days. Those first questions were like really easy, and now all of a sudden it's like, okay, well, it's gotten significantly more, let's say, interesting between that first page and the second page. Are there any questions before we continue? All right, turn the page. Here we go. So this first example, we're definitely going to do together. And you'll see some directions off to the side there. And we're just going to follow those. So what is the sum? Here we go. Follow along closely with this one. What is the sum of x plus 3 over x squared minus 1 and 2 over x squared minus 3x plus 2? follow a similar procedure to the one you used to add numerical fractions with unlike denominators. So basically, we have to figure out a common denominator and then add together the numerators. So at its base, that's what we're doing. But in order to figure out our common denominators, we need a least common multiple, which we just practiced on the previous page, which means we have to factor the denominators to make that happen. So the first thing we're going to do is factor each denominator. So if we factor the first denominator, x squared minus 1, that is a difference of squares. So that'll be x plus 1 times x minus 1. So we're going to get x plus 3 over x plus 1 times x minus 1. That's what that one factors to on the denominator. And then the other one, we're going to say plus 2 over, what are we going to end up with here on the denominator for this one? What does that denominator factor to underneath the 2? You're going to multiply to a positive and add to a negative. What does that tell you about the factors? Yeah, they're both negative. -1 and -2. Yep. So x minus 1 times x minus 2. All right. Now we're going to use those denominators to figure out our least common multiple. And then we have to multiply each of the fractions by the missing piece of the least common multiple, just like we do with regular fractions. So first of all, what is the common denominator here? What's the least common multiple going to be? How many distinct binomials do we have? Three, right? Three distinct ones, right? Because the x minus 1 is on both of them. So there's one of them. X minus 1, that's one. X plus 1, that's the second one. And then x minus 2 is the third one. So this first fraction needs to be multiplied by what to create the common denominator? Which one is it missing? X minus 2, exactly. So down on this next line, we're going to write leave a little bit of space to the left. And we're going to write x minus 1, or sorry, x plus 1 times x minus 1. And then this one needs to be multiplied by x minus 2 because that's what's missing from the denominator. Yeah. I should have written x plus 3. Yeah. Thank you. I'll change that. X plus 3. All right. And then on the numerator and denominator, we're going to multiply by the missing binomial, which is x minus 2. So numerator and denominator get multiplied by that. And because we have to multiply the numerator and denominator because we don't want to change the value of the fraction. And we talked about this yesterday. When you multiply the same thing on top and bottom, it just means you're multiplying by 1. It's a unique form of 1. And then we're going to add. Now the 2. X minus 1 times x minus 2. What do we have to multiply this fraction by to get our common denominator? X plus 1. Good. So top and bottom, numerator and denominator get multiplied by x plus 1. Doing that gives us the same 3 binomials on each denominator, which creates a common denominator. Everybody okay with that? This is where we're at so far. Any questions on this at this point? Okay. So now I'm going to put parentheses around the x plus 3 because on the numerator on this one, we're going to have to use FOIL. Over here, we'll just distribute the 2 to the x plus 1. We are not going to multiply out the denominator. We're going to leave that in factored form. And we're going to end up, if we can, we're going to end up factoring the numerator if we can as well, and then cancel some stuff out. But in the numerator only, multiply the factors and like terms and factor again. So we're going to combine like terms after we multiply out and then factor it again if we're able to factor it. So over on the left here, let's do our FOIL here. So that's going to be x squared. So here's our new numerator here, x squared. Let's see, that's 3x and negative 2x. 3 minus 2 is 1, so that'll be positive x, so plus x. And then negative 2 times 3 would be minus 6. So that's foiling the numerator here. That gives us to write that. And then we're going to add 2x plus 2, because if you distribute the 2, that's what you get, 2x plus 2. So plus 2x plus 2 over our common denominator of, doesn't really matter what order we write these in. I'm just going to go x minus 1 times x plus 1 times x minus 2. As long as we include all three of them on the denominator, we're good. So we've consolidated everything onto a single numerator because we now have a common denominator. Any questions about that step? These are the exact steps that we do when we add regular fractions. It's just we're using polynomials now instead of just regular numbers. So it's a, we're using a lot of algebra to get here. But I honestly don't think anything that we're doing is something that you've never done before. It's just doing a lot of it in one problem. All right, now let's combine some like terms. So x squared, there's no other squared on the numerator, so that'll be x squared, that'll stay. 1x and 2x, that'll be plus 3x. And then negative 6 plus 2 would be minus 4 over x minus 1 times x plus 1 times x minus 2. Now, try to factor the numerator. We have two numbers that'll multiply to negative 4 and add to positive 3. How about negative 4 and 1? Yeah. How about 4 and negative 1? Sorry, not negative 4 and 1, but 4 and negative 1. Because positive 4 and negative 1 would add to positive 3. Negative 4 and positive 1 would be negative 3. So positive 4 and negative 1. So it'd be x plus 4 times x minus 1 over x minus 1 times x plus 1 times x minus 2. By the way, once we consolidate the numerators, we're basically doing what we did yesterday in terms of simplifying. So we're trying to factor it and then cancel out anything we can. So make sure, yes, we are going to include this addition one. Yeah, we are going to include values of x that won't work. So values of x that will not work for this, what are they? So it says simplify and state the domain. So the domain is going to be all real numbers except for x equals what? 1, what else? Negative 1, what else? 2, good. Three numbers that x cannot equal. 1, negative 1, and 2. So x minus 1's cancel because we got 1 on each numerator and denominator. And so our answer is going to be x plus 4 over x plus 1 times x minus 2. And we're going to say for x not equal to negative 1, 1, or 2. There's our answer. We're stating the domain once we get to the addition portion. I think now you understand why I gave so much extra space on these next two questions. These are not short problems to work on. We've got 9 more minutes today, so we might just do A together, and then I'll have you start off tomorrow working on B on your own, and then we'll keep going after that. We'll finish up the next examples tomorrow as well. We'll finish it up, and you give it a little bit of time to work tomorrow, and then Friday will be a complete work day. So let's work on A. Let's keep going here. So what's our first step? What do we have to do? Factor the denominators. Good. So this is going to be x plus 6 over what? What is that denominator factor to? Good. X plus 2 times x minus 2. Nice. Plus 2 over. Will be another binomial here. Go ahead, set x there, x there. What are our two factors that we're going to use in those binomials on the denominator for factoring? 3 and 2, both negative? Yeah. So x minus 3 times x minus 2. All right. how many binomials do we need for our least common multiple? Listen up. How many binomials do we need for our least common multiple? 3, yeah. X plus 2, X minus 2, and X minus 3. So the one on the left gets multiplied by X minus 3 on the numerator and the denominator, because that's the one it's missing. What one is missing from over here? What are we multiplying by on the other fraction? X plus 2, good. So this one gets multiplied by X plus 2 on the numerator and the denominator. Great. Now we're going to go ahead and FOIL on the fraction on the left and distribute on the fraction on the right. So go ahead and do that step. And then put everything over the single LCM. I'll go ahead and draw a line here so that when we work on B tomorrow, we won't get things mixed up with column. Well, how's this looking? We should have X squared plus 3X minus 18 plus 2X plus 4 over the 3 binomials in no particular order. So if your denominator has those 3 sets of binomials, that's fine. If they're not in that order, it doesn't matter. As long as you have all 3. Okay, what's next? Combine like terms. All right. So if we combine like terms, that's looking like X squared plus 5X minus 14. All right. Do we factor the numerator? If so, what does it factor to? Seven and 2, which both positive, both negative, one of each. Good, negative 2 and positive 7. So X minus 2 times X plus 7 over X minus 3 times X plus 2 times X minus 2. All right. We got a common binomial on the numerator and the denominator that we can cancel out. X minus 2's will cancel. So we're going to be left with X plus 7 over X minus 3 times X plus 2 for X not equal to what values? Negative, yeah, 3, negative 2, and 2. So I usually write mine from least to greatest, like I mentioned yesterday. It doesn't matter if you do or don't. I just like to have that order to it. That's our answer. That took a lot less time. It took about the same amount of space on the paper, but it took a lot less time. So I think we'll go ahead and stop there for today. We'll start off with part B tomorrow. I'll have you try that one on your own when we come into class tomorrow. That'll be your warm-up tomorrow. Will be B for that.